Most robots built today share a single fatal design flaw. They rely on a centralized body. If you sever a single leg or damage the main torso, the entire system shuts down. Look at these complex humanoid robots. Every wire and sensor routes back to a single point of failure. If one critical component breaks in the wild, the machine becomes dead weight. Researchers at Northwestern University recently built what they call a legged meta-machine. When this machine is chopped in half, both severed halves fluidly rebalance and walk away in opposite directions. By abandoning the idea of a central torso, these engineers have bypassed the fragility of traditional machines. They have built synthetic structures that react to trauma the way biological organisms do, by adapting and surviving. Northwestern's meta-machines are composed of independent units called autonomous modular legs. These units can be freely attached to form a larger collective body. This diagram shows the internal anatomy of one of these modular legs. Inside the central spherical joint, there is a printed circuit board, or PCB, which acts as a localized nervous system. A PCB is a physical board that connects and coordinates electronic components. The sphere also houses its own battery for a metabolism and a motor that acts as its muscle. These individual modules are mechanically simple, only rotating along a single axis. When you bolt several of them together, they combine their single degrees of freedom to create agile, multi-legged locomotion. Because every leg processes its own movement and carries its own power, the intelligence is entirely distributed. There is absolutely no master brain to destroy, which makes the whole robotic structure virtually impossible to kill. This creates an immediate logistical problem. If you chop off two of its legs, how does the remaining decentralized body instantly know how to walk without falling over? Researchers solved that problem by training an amputation-agnostic policy. An amputation-agnostic policy is an AI control algorithm trained to maintain locomotion regardless of what parts of the body are missing. They placed digital versions of the robots into a Darwinian computer simulation and subjected them to millions of damage scenarios. When a digital limb is severed, the algorithm doesn't fail. It immediately recalculates the machine's remaining mass, adjusts the torque of the surviving motors, and invents an entirely new walking strategy on the fly. Testing this policy in the real physical world showed that the meta-machine remains mobile despite deep structural damage. After losing one hind limb, the physical robot actually moved at 105% of its original speed. By compressing millions of generations of evolutionary trial and error into an AI simulation, engineers have created a digital brain capable of surviving the unsurvivable. This evolutionary training resulted in a behavior known as kinematic self-destruction. If the machine sustains damage that inhibits its movement, or if it finds itself with a redundant limb that slows it down, it autonomously identifies the problem. The robot deliberately thrashes the dead weight against the ground until the joint snaps completely off. Once freed, the reduced body walks away faster. The severed module isn't dead either. Thanks to a protocol called roll home, a detached limb, which still possesses its own battery and motor, becomes an independent agent. It can actually roll or jump back toward the host body. Self-amputation and independent regeneration are traits we usually observe in starfish or lizards. Seeing a machine sacrifice its own body parts to optimize its survival suggests a set of instincts previously exclusive to the natural world. We now have metallic structures, capable of modular reproduction, instantaneous adaptation via artificial intelligence, and decentralized survival after dismemberment. This industrial robotic arm represents the traditional model of engineering. It is massive, static, and locked into a single predetermined shape. But these new meta-machines can evolve their own body plans, sever their own limbs to survive, and heal themselves while navigating the wild. The distinction between a rigid technological tool and a resilient synthetic life form has permanently blurred.